Students, are you there?
Yes, sir.
Yeah, my voice is audible, Babu.
I'm interested.
Okay, fine. So before going to the behavioral modeling, so let us a small topic is pending in the last class. That is the delays in switch level modeling. Delays in switch modeling. Switch level modeling. So this is actually pending concept. It's not pending concept means delays modeling. It's just name I am giving that we have not discussed this topic in the last class. Okay. So anyway, the gate delays that we have seen and the delays that we have seen in data flow modeling as well. Now we are going to look at the delays in switch level modeling. Okay, the same whatever the delay concepts that we have used for the gate level modeling and data flow modeling, all these things are applicable to the switch level modeling as well. That means the switches as well, except uh, except bidirectional switches and resistive switches. Okay, so therefore what we can say that all the delay concepts are applicable to regular switches. Okay. But for bidirectional bidirectional and resistive switches, except for, it's better to write except for. Okay, so therefore what is the delays that we are applicable to the regular switches, data flow and gate level modeling? So zero delay, without delay, instantaneously the output will be generated, or otherwise one delay, two delay, three delay. So these are the delay informations. Okay, zero delay, one delay, two delay, three delays are possible for the regular switches also, but for the bidirectional and resistive switches only applicable for zero delay or one delay or two delays. Okay, so delays applicable for bidirectional or resistive switches are, the one is zero delay, of course, without giving any delay, or one delay and two delays. Okay, so but these delays are mostly the name of the delays. Let us write the name of the delays. So this is what we have to remember: turn off, and turn on. So turn off and turn on delay. So these are the delays that normally we come across for this switches. Okay, normally we have a raise delay, fall delay, turn off delay, right? But here we see that turn off delay and turn on delay. Okay, zero delay stands for that we are not applying any kind of turn on and turn off delay. One delay stands for if you are giving only one delay. For example, something like this. For example, tran. I think it's tran. Okay, so give some delay. For example, two delay. For example, okay. So the name of the gate is, for example, N1. For example, okay. What is there in it? Output we have to write, and then we need to write input. Okay, output and input we should write. So therefore, the two stands for, it is for both the turn on and turn off. What is the turn on and turn off actually? So therefore, turn on means generally from uh, it is from zero. Sorry, normally the switches are actually operated for either a high impedance state or on state. Okay, that means it has to move from high impedance to the logic 1 or high impedance to the logic 0. There is a possibility. That means the information can go from high impedance state to Z to a logic 1 or Z to a logic 0. Okay, so these are the two things are there. Okay, so any value to the unknown value can be treated as a turn off delay. Any value to the known value, we can call it as a turn on delay. Okay, so turn on and turn off can be defined in this way. Therefore, when you write the moment, if you write a two, turn on and turn off delay both are same. For example, if I'm write something like this, therefore what we can say that here two delays that we have used, two delays we have used. Sorry, I'm sorry. It is one delay only. Okay, so one delay only we are using. Similarly, if you're using the tran, for example, tran of 2 comma 1, for example, and n1 and 2, for example, I'm writing. So if I write output comma input, if I write like this, okay, then how many delays that we have introduced here? Two delays. Okay, two delays. That means turn on delay is 2, turn off delay is 1. So the first one is turn off, turn off. The second one is, sorry, turn on, turn on, turn on, and second one is turn off. Okay, that's what we can say. Similarly, for example, if you're not writing anything, for example, tran, for example, tran, if you're writing tran n1 output comma input, if you write like this, for example, okay, then how many delays that we have assigned here? Zero delay. So we have not mentioned any kind of delay. Instantaneously the output can be generated. Okay, these are the bidirectional switches. Similar concepts are applicable for the resistive switches as well. Okay, so therefore it is important to note that except for the bidirectional regular switches, the turn on and turn off delay will be applicable for this one. Okay, next. The next one is let us go for the behavioral modeling. It's a very important modeling style. So let us discuss about the behavioral modeling. So this is a very important modeling style. Almost every digital book will explain the verilog code based on this particular modeling style only. Okay, so behavioral modeling. So one of the important thing about this one is it is a high level programming language. Okay, it is a high level modeling style actually. You can simply say that. It is a high level modeling style. What do you mean by high level modeling style? That means we don't bother about the internal circuitry of the system. Only we can understand the logic of the system. Okay, how it works, what is the input output behavior. So far we have seen that gate level modeling. In the gate level modeling, what we identify that uh, that means gate structure is important. Okay, so when we talk about the complexities increases if the the complex, if the number of gates are increases, right? So therefore we have gone for the data flow modeling. Therefore there also we talk about the two possibilities. One is that based on the mathematical equation. Therefore, we have to develop the mathematical equation. From that one, we can generate the hard. From that one, we can write the program. So sometimes it is also possible just by writing the input-output behavior. Okay, by knowing the input-output behavior, it is possible to write. But input-output behavior is well defined in behavioral modeling. Okay, so therefore that is the concentration that we have to maintain. Okay, therefore we have to put our concentration on input output behavior logically. Okay, therefore by using the procedural statements, this information can be written very perfectly. Okay, so that means that what I'm going to write with the help of here, the description is based on description is based on input output behavior. Input output behavior. Okay, so this input output behavior is described by using the mathematical equation in the data flow modeling. But here we are going to write in the form of a procedural statements. Okay, that's the point we have to remember. So this behavior is well defined with respect to procedural statements. Procedural statements. Okay, so therefore we are going to use some procedure in previously assignment statements that we have used, but a procedural statement we have to use in behavioral modeling. Okay, so therefore what are the available procedural statements? So available procedural statements. Number one is if statement. Number two is if else statement. Number three is case statement. Number four is uh, loop, for loop, etc. So many are there. We will discuss all the things one by one depending upon the application. Okay, which one is the best possible way that we can write, we can use it, that one. Okay, so and it is very important to note that these procedural statements must use within always and initial blocks only, either always or initial blocks, always or initial blocks. So if you want to use the procedural statement, we have to know, we have to write within the always or initial block. That one, this is the setup block which where we are writing the procedural statement. Therefore, whenever you are writing the behavioral modeling, you should keep in your mind that there should be either always block or initial block. But on 99% all the digital designs that are right in the behavioral modeling within the always blocks only for the design description, whereas for the test bench descriptions we use the initial block. Okay, normally the normally we write the test benches in the form of behavioral modeling only. So with the behavioral modeling only we write all the behavioral modeling only, we can write all the procedural statements within that one. But just you have to remember that always block is meant for design description, initial block is meant for test bench description. Okay, so that is a blind notation that we can understand. Okay, for the simplicity I'm writing here, it always block is preferable, always block is preferable for design description. Okay, most of the cases. It doesn't mean that we don't want to use this always block in the test benches. Okay, test bench writing, we can also use that one also, but preferably we have to use always block in the design description. Initial block, initial block is preferably for test bench description, test bench description. Okay, that's what you have to remember. Okay, so whenever you're using the always block or initial block, it is mandatory to consider initial begin and end blocks, sub blocks. Okay, whenever we use always block, always or initial blocks, begin and end begin and end block is necessary. Not necessary means which means that when two or more statements are there, so two or more statements, if a single statement begin and is not necessary to write, but if we have a more than two procedural statements or two statements if you are writing, then a begin and end block is to be required. Okay. Okay, if more than, I can write it for simplicity, if more than two statements, if more than two statements. Okay, fine. So this is what actually the basics related to the behavioral modeling. What do you mean by the behavioral modeling? Uh, of course, for the input-output behavior is described with the help of this modeling style. If you want to describe it, what are the things that are required? Procedural statements are required. So where we need to write the procedural statement means initial and always block. Within the initial or always block, I need to write this procedural statement. Without initial or always block, we are not able to write. We should not write any procedural statement. The next one is it is mandatory to consider that begin and end block subblock is necessary if we are writing the two or more statements. Okay, so this is the fundamentals related to the behavioral modeling. So let us go quickly for the writing a Verilog program in the behavioral modeling. Okay, and one more thing is that behavioral modeling is applicable for all the digital circuits, whether it is a combinational circuit, whether it is a sequential circuit, it doesn't matter. Okay, so it is applicable for all. So in case of in case of combinational circuits, for example, in case of combinational circuits, if it is in the data flow modeling or whether it is in the gate level modeling, better to go for gate level modeling or maybe the data flow modeling, not a behavioral modeling. Okay, so I'm sorry, actually we have to write uh, the behavioral statements exclusively for the sequential circuit as well as combinational circuit. But when we are dealing with the sequential circuit, the data flow modeling and gate level modeling is not applicable. Okay, not applicable means it's not advisable to do this one because the output is depending upon the previous state. Okay, so that statement is also we can write it here. So behavioral modeling is applicable for behavioral modeling can be used for combinational and sequential circuits sequential circuits. Okay, so it is better to write this one, combinational and sequential. Okay, whereas this data flow modeling or gate level modeling is meant for combinational blocks, but it's not advisable for sequential blocks. So it's also very important. So data flow or gate level modeling is meant for best suited is best thing where to write, best suited for combinational circuits, but not good for, but not advisable for sequential circuits. Sequential circuits. Please remember this point. Okay, because for the sequential circuit output depending upon the previous value. Okay, so that's the reason why it is difficult to write the data flow modeling or gate level modeling for the sequential circuits. Okay, so best way is that we have to the behavioral modeling. Okay, is it clear to all of you? So the data flow modeling, what circuits we are able to model them by using the behavioral modeling, what circuits we are able to model for the data by using the data flow as well as gate level modeling. Okay,
Yes.
okay, fine. Let us take one example. So that much theory is sufficient for the behavioral modeling. Let us take one example. We start with a combinational circuit. Okay, then we'll go for other thing. Or better, we write some sequential circuit only. Write a Verilog program. Write a Verilog program for D-latch. For a D-latch using behavioral modeling. Behavioral modeling. First, we write some sequential elements and then write the sequential circuits. Then we'll go for the combinational circuits. That's the best way to write, understand the behavioral modeling. First, we write the sequential elements related behavioral modeling. Then we'll go for sequential circuits related behavioral modeling. Thirdly, we'll go for combination circuit behavioral modeling. Okay. Okay. So everybody knows that. What do you mean by a sequence D-latch? Okay, so we take the deal as something like this: a black box having one input is called DAN input. It produces a D output signal when enable signal is equal to true. When enable signal is equal to true. Okay, so therefore, what is the logic behind this one? Let us write here logic. What is the logic, or what is the functionality? So logic or functionality. So if enable signal is equal to 0, for example, if enable signal is equal to 0, D out will be previous value. D out should be in the previous value only. So whatever the previously, that since it is a latch, it's a memory element. That means whatever the previous value is there, that previous value will be retained. So the D out is equal. D out means that the content of the latch is not at all changed. Okay. When the enable signal is equal to true or enable signal is equal to 1, and the D out is assigned by DAN signal. D out is assigned by DAN signal. So this is what the operation or behavior of this particular D latch. Clear? So therefore, how do we say that this is a memory? Because the contents are not changing means it is in the storage state. Storage state. Okay. So when the information is transferable means it is a transparent mode. Transparent. Okay. So therefore, it can store as much as possible. It can transparent when it is required. Okay. So therefore, it is best explained with the help of logical diagram. How what exactly the meaning of this one? Okay. For example, the input is something like this. For example, I have an input is something like this. Okay. Now, so this is my enable signal. For example, this is my enable signal. Okay. Now the input is something like this. Okay, the input is something like this, for example. Okay, this is called input, DAN. I want to define my output, D out. What is my D out? What should be my D out? Okay, so let us apply this logic here. So what is the logic says that if the enable signal is equal to 0, so what is happening here? If the enable signal is equal to 0, that is what we are observing that. So irrespective of the whatever the input it is, the output is the previous value. What is the D out value previously that is available? Since it is a memory element, we don't know what is the previously that is available. Okay, so that's the reason why we don't know what exactly happening in that one. Okay, so this is happen as long as the enable signal is equal to 0. So therefore that value is unknown value. We don't know what exactly the value is available previously, since it is a memory element. Fine. So at that instant of the time, that means there is a enable signal is equal to high. When the enable signal is equal to high, what is the data that we observe here? that is 0. Okay, so therefore as long as the enable signal is equal to high, if you see that, as long as the enable signal is equal to high, okay, so the DN input signal is equal to D output signal. Okay, so therefore D output signal is how much value this is. From here to here, the DN signal is there. DN signal is from low value, high value, low value, high value, something like this. As it is, information must be transferable. Is it clear? As it is, information must be transferable. So I can write this is in this way. So therefore that value is equal to low, this value is high, this is low, high, low, high. Clear? So that is how it will be transferable. So DN input signal will be transferable in this way. Now here you look at the next one. So we have see that the enable signal is equal to low from here to here. Okay, the enable signal is equal to 0 from here to here. So from here to here, the enable signal is not there. So what it can observe, whatever the previous value is there for the D out, that will be remains there. What is the previous value in this case? This is the one previous value, right? So this is retains there up to the next positive next value of the enable signal. So that value is remain, that will be retained. So the previous value is retained. Clear? Again, you can see that there is a possibility of low signal. There is a low signal is also observed here. Sorry, I'm sorry. It is a high signal is observed here. So what is happening here? Enable signal is equal to high. Therefore, what is happening? Chapala. What is happening here? So therefore, up to this point, this value is equal to high only.
DN is called D out.
Yeah. So up to this point. So what the DN is equal from here to here, you can observe. This from here to here, it is under the enable high value only. So that will be transferable. Okay. So that will be transferable. It will go to low and come back and again go high, low, high up to this point. Okay, therefore it is low means so again it will be going, it is the continuous to the next level as well, because the previous value will be retained for this level. Okay, so for this level low value will be there. So this is how the information will be transparent or maybe stored within the latch. Okay, now this is what actually the behavior. Therefore, we don't want to consider this waveform and all other things. But whenever you are writing the test bench, this waveform is necessary. Okay, whenever you enable, we have to give something like this for some value of the enable signal. For example, 0 time enable is equal something like this. For example, 0. For example, it is 5 nanoseconds. For example, it's 20 nanoseconds. For example, it is 40 nanoseconds. Okay, I think it's better to consider the 15. It is considered the 15. It is considered to be 35. It is considered to be 45, 55, for example, something like this. Okay, so therefore we have to write A and B, enable and DN signal in the test bench, and we have to expect the output as shown in the bottom one. Okay, so therefore if you know the concept, then you can understand what output that we have got, whether we got the desired output or not according to our description. Okay, now so whenever you are writing the program, this is very important for us. Okay, the important thing is that this is important. Okay, this is important. Okay, let us write the program accordingly. Copy and then paste here. So this is how the input output behavior. Let us write a Virla program. Please carefully understand. This is a very, very important modeling style. Okay. Now let us start with this. This is also a simply module. Okay, let us write the module here. Module. This is called DAN. We have a D out. We have an enable signal EN. Okay, let us write a module name. It's a module. It's a D latch. D underscore latch. We should not give any kind of space. D latch Okay, so what is the enable signal? What are the signals that we are using? DN, enable, and dout. Okay, next inputs are DAN and enable signal. What are the outputs here now? Only one output, that too dout. Okay, so I'm going to write the behavioral modeling. Okay, we have seen previously we have to use always block. Without using the always block, it's not possible. Okay, always at the rate of some sensitivity list I need to write. Okay, that means this the whatever the procedural statement that we write here. Okay, so let us try to begin and end here. So whatever the statements I'm writing in this between the begin and end, these statements are executed based on the changes of a particular variables. Okay, then only these blocks are these statements are executed. So without writing the sensitivity list, or without writing the output dependent variables in the always block, it is not possible to execute the begin and end statement. Okay, so it is mandatory to write when we are describing the circuits. It's not necessary for the test bench writing, but it's necessary for the digital descriptions. Okay, now output is depending upon what factors you can see here. The output is completely depending upon the changes of the input signals, because the changes of the input signals. Okay, so here we can see the changes from low high, something like this. So therefore these changes also will be traced. One more thing is that the changes of the input also, whenever there is a change in the enable signal, whenever there is a change in the DAN signal, then only things will be happening, output can be evaluated, right? So without change in the enable signal, without change in the DAN signal, it's not possible to do that one. So therefore what I can do is that, so therefore the output is completely depending upon the DAN signal. Output is depending upon DAN signal, sorry, DAN signal, and as well as enable signal. Comma I can use, or OR also I can write, but usual practice is comma is more than sufficient. So DAN comma enable signal. So whenever there is a change, okay, at the rate symbol stands for, there is a change. Whenever there is a change in DAN, whenever there is a change in enable signal, the following circuit has to be done. Therefore, the following circuit has to be executed, or following procedural statement has to be evaluated. Clear? So what is the statement that I can write as simple statement? I'm using the if statement. Okay, the procedural, one of the procedural statement is if statement. I'm using the if statement. For example, I'm writing like this: if small letters only, if enable signal is equal to true. Okay, so better I need to write in different color. Enable signal, if enable signal is equal to true, if I'm opening that one and writing something. Okay, so therefore if better I can write the syntax for if here also. Syntax, if I can write if an expression, and then you need to write assignment, and we have to write assignment 1. Okay, or assignment 2, or we can write assignment 2. See, you can carefully understand that the moment if I'm writing if assignment is 1, if expression is true, the first statement will be executed. Okay, so therefore after that, if it is true, the first statement will be executed. If it is false, I did not write else statement, therefore it cannot do anything with that one. Just after the execution of the first statement, it will go to the second statement without evaluating the expression. Okay, so for example, if the expression is true, the following circuits has to be executed, means we have to write the curly brackets. But in Verilog point of view, we don't write the curly brackets. So instead, we can write the begin and end statements that we need to write. Okay, so we have to write begin and end. Okay, so this is what we can write. So we can write here is begin, and end. Okay, therefore if the expression is true, for example, in this case, two statements must be executed. Okay, if expression is false, no other statement, third statement is there, therefore it cannot be executed. Therefore only that will be, if expression is true, this is happening. If expression is false, whatever the previous values for the assignments are there, those previous values will be retained. Clear? So therefore, if the enable signal is equal to true, what has to happen? You can clear them. What has to happen? As we have seen that if enable signal is equal to true, the data in is equal to data out. Ante kada jaragalsindi. The transaction has to be takes place. Therefore, I can write d out is equal to tan. As simple as that. If the enable signal is equal to true, the thing has to happen. So if I'm not writing enable is equal to false statement, for example, the d out will be the remains in the previous one only. Okay, if I'm not writing the else statement, no, don't worry about it, because if you're not writing the else statement, if the false condition, if you're not writing, the d out is available whatever it previously it has got. Okay, so that is the information is default the if statement has done for the latch. So therefore if statement is normally applicable for the d latch directly.
సార్ ఈఎన్
Okay,
జీరో
so
గానే
therefore
మనకు ఇవ్వాలి. ఇఫ్ ఈఎన్ ఈక్వల్ టు
what we say that what yeah,
ఈఎన్
that is
కి
also can be written. Yeah, so for example, if I am saying that if enable equal to 1, okay, if you want to say it like this, it is equivalent to say that if enable and if within the bracket enable, both are equal. That means if the expression is true, okay, if for example if I'm writing like this, if not of enable, for example, okay, so this condition is true, this condition can be true or it can be false. Okay, if this condition is true, certain statement is executed. If it is false, some other statement will be executed. The question is that how we are assigning the enable value, right? So this enable value is assigned in the test bench.
సార్
Okay,
నెగేషన్ అయినా వాడచ్చు సార్. నెగేషన్
yeah, negation also వాడుకోవచ్చు. For if negation వాడితే ఏమవుతున్నప్పుడు నాకు what we can observe, if the if I'm writing the negation, for example, negation of enable signal. Okay, if statement is enable, if enable is equal to 1 I have given, for example, then what is happening here? If not of 1, so what is happening here? That is false, right? It is a false statement. If it is a false statement, is what is happening here? The previous value will be there, right? Previous value of the d out is will be a previous value. If enable is equal, that means it is actually d out is equal to d out అవుతుంది అంతే కదా. d out is equal to d out. If enable is equal to 0 అయింది అనుకోండి, అప్పుడు ఏమవుతుంది? So therefore it becomes if not of
ట్రాన్స్మిషన్
0.
జరుగుతుంది.
So if it is true, true means what is happening here? d out is equal to dn, but it is contradictory to our logical information, right? ఓకే, అవర్ రిక్వైర్మెంట్ ఏంటి? మన రిక్వైర్మెంట్ ఏంటి? ఎనేబుల్ 0 అయినప్పుడు సేమ్ ఉండాలి, స్టోరేజ్ ఉండాలి. ఎనేబుల్ 1 ఉంటే ట్రాన్స్ఫర్ అవ్వాలి. కానీ ఇక్కడ ఏమవుతుంది? డిఫరెంట్గా వస్తుంది. దట్ మీన్స్ వాట్ ఈస్ వీ కెన్ కాల్ ఇట్ యాస్ ఇట్ ఈస్ ఎ నెగటివ్ ల్యాచ్. Okay, so therefore knowingly or unknowingly some doubt we have erased, so this is called actually negative latch. So the previous one is actually a positive latch. So the positive latch says that when enable signal is 0, the storage has to happen. If enable is equal to 1, the transaction has to be takes place. In case of negative latch, if enable signal is equal to 1, the data should be remains there. If enable signal is equal to 0, transaction has to be happen, right? So therefore anything can be possible. Just we have to remember that. ఓకే, మనం ల్యాచ్ అనేది పాజిటివ్ లెవెల్ బేస్డ్ ట్రాన్సాక్షన్ ఉంటుందా, నెగిటివ్ బేస్డ్ ట్రాన్సాక్షన్ ఉంటుందా అనేది డిపెండింగ్ అపాన్ యువర్ రిక్వైర్మెంట్. నాకు పాజిటివ్ ల్యాచ్ కావాలి. ఓకే, పాజిటివ్ ల్యాచ్ కావాలంటే నేను ఏం చేస్తాను? ఎనేబుల్ ఉన్నప్పుడు ఏం చేస్తాను? నేను ట్రాన్స్ఫర్ చేస్తాను. యాక్టివ్లో ఎనేబుల్ సిగ్నల్ ఉన్నప్పుడు రీటైన్ చేస్తాను. నాకు కాస్త నాకు నెగిటివ్ ల్యాచ్ కావాలి నాకు అన్నాను, అప్పుడు ఏం చేస్తాను? నేను పాజిటివ్ ఉన్నప్పుడు స్టోర్ చేస్తాను, పాజిటివ్ ఎనేబుల్ ఉన్నప్పుడు, నెగిటివ్ ఎనేబుల్ ఉన్నప్పుడు 0 చేస్తాను, స్టోర్ చేస్తాను. ఓకే, సో ఎనీథింగ్ కెన్ బి పాసిబుల్. సో దేర్ఫోర్ ఎనేబుల్స్ వాల్యూస్ ఎట్లా వస్తాయి దీనికి? ఈ ప్రోగ్రామ్ కంటే అక్కడ నుంచి టెస్ట్ బెంచ్ రాస్తే అక్కడ నుంచి వరకు వస్తాయి అనమాట. ఓకేనా?
ఓకే సార్,
ఫైన్. సో దిస్ ఇస్ హౌ వీ కెన్ రైట్ ద డేటా ఫ్లో behavioral modeling for the D latch. positive delatch, in fact, actually. Okay, let us write, but you can see from this diagram, the storage capacity, the storage duration is very less here. Okay, so where we can identify the storage. So whenever we have a storage is observed here. Storage is observed here. The storage is observed here also. So, but my requirement is that the storage will be as large as possible, but the transaction is only at the instant of the edges only. Okay, so that the transactions only required for the edges only. That means here only the edges only. Here the edges only I want to consider, but the remaining time everything must be storage purpose only. Okay, therefore whenever we are storing the information based on edges, okay, this is called a flip-flop instead of calling a latch, right? So let us talk about the latch now. So let us take the same diagram so that more clearly we can understand this one. So for example, this is the diagram. See, for example, I want to discuss about D latch, D flip-flop. Okay, so therefore the flip-flop is nothing but what we are going to do is that, so forget about the flip-flop, whether it doesn't matter, but the name is a different issue. But the thing is that I want to increase the storage time. Okay, so throughout the period that I want to store, only half of the period only I'm storing, but I want to store the information throughout the period. Okay, so then how can I do this one? Okay, so this can be done, for example, this can be done. So the storage has to be takes place during this time. ఇక్కడ నుంచి ఇక్కడ మొత్తం నాకు స్టోరేజ్ కావాలి. Okay, storage. Okay, that means for every positive edge I need to have that means for entire period that I want to store the information. Okay, storage. But transaction has to be applied only at the edges. Okay, only at the edges I want to transfer the information. Okay, remaining times that must be storing the information. Clear? So what is the requirement is that? The requirement is something like this. The enable edge for data transmission, for data transmission. Okay, remaining cases for storage, data storage. So this is what the logic behind this one. So if any device is operated on this particular logic, that is called a flip-flop. And manamanta babu, flip-flop. Now we are going to talk about a D flip-flop, exclusive to the D flip-flop, for simple understanding. So at the edge only I want to consider. Okay, so since here also this is also a memory element, therefore we don't know anything about the available information. Okay, so therefore what I can say that just you have to use the same notation. So forget about this this D out, but the D out is here is actually D out for flip-flop I'm writing here. Okay, so at this instant of the time we can see the unknown value. Here also it is unknown only. Here also it is unknown only. Whenever it encounters the positive edge, up to that point, we don't know what is the previously that is available. Okay, but here at the instant of this positive edge, you can see only one data. You can see only one data. That value is 0 only. That value is 0 only. Okay, so therefore 0 will be assigned here now. 0 will be assigned here. 0 will be assigned here. This 0 will remains there up to the next positive edge of the clock or enable signal. Okay, therefore this retains there up to the next positive edge of the enable signal. Clear? Up to the next positive edge of the enable signal. Okay. So for simplicity, what I'm going to do here is that I want to change this one. Of course, okay, but let it be like that only. So what is the output here now? Again, what is the output? So and again, we can see a positive edge here. We can see a positive edge here. So at this point also, we can see a logic 0. Again, that logic will be retained, will be assigned here. That logic 0 is assigned here. That will be continuous for the next positive edge to come. Okay, therefore it is not that much understandable. Therefore I want to change this particular scenario with another one. Okay, so that information is something like this. I can remove this one also, is better. Okay, I'll write this way. Changes here, but change is observed. Change is observed here. Will change from here also. Something like this. Okay, I'm unable to remove this portion, so please try to understand. If I remove this one, the entire thing will be gone. Okay, but anyway, any input signal is not a matter here. For example, something like this. Okay, so what is happening here? What is the modification here? You can observe. What is the modification? Here the signal will be changed something like this. So it's not required. So accordingly, this one is something like this. At the positive edge of this one, we find a logic 1. Okay, we find a logic 1. What is the value of the output? Logic 1 will be assigned here. Okay, so that will be continuous throughout the period. That will be continuous throughout the period. Okay, therefore you can see very carefully. So one period from this positive edge to another positive edge, we can call it as a period. Okay, it's a period, time period from here to here. Okay, so during that period, the information is stored here. Okay, this is the storage time. Now this is the storage time. This much value, the one period. Here also from here to here, the storage time. So by using the edge flip-flops, the storage time will be increases, and the information we are taking at the edges of the data only, at the edges of the enable signal only, no other places. Okay, so therefore that is how actually normally nowadays the people are using the storing purpose. People are using the flip-flops than the latches. Okay. Now the question is that small modifications are there. Instead of whenever you are calling the flip-flop, instead of we can call it as enable signal, we will call it as a clock signal. We will call it as a clock signal. Okay, and since the edges are also there, therefore the symbolic representation of the flip-flop is something like this. Flip-flop symbol. So please wait for 2 minutes, then I will complete it. Okay. So for example, we take a flip-flop here. So data in is as usual, data in, and we have a data out. Fine. So we are going to use an edge signal, right? Edge of the clock signal, what I'm going to write, CLOCK clock. Okay, so this is called a flip-flop. This is called a flip-flop. Previously, we can call it as a latch. So it is a latch. So latch is sensitive, but flip-flop is a edge sensitive. That is why the people are calling it as flip-flop is edge sensitive. Sensitive in the sense the data is transferable or not, the data is taken into consideration or not. That is called sensitivity. Okay, so the flip-flop is edge-based sensitivity. That means at the edge the transaction has to be takes place. where the enables for in the case of latches only at the throughout the duration of the high level or low level the transaction is to be takes place. Okay, let us write a Verilog program for this one and we can stop. Okay, so let us write the Verilog program. So let us write a module D flip flop. So what are the things here? We can see DN signal, CLOCK clock, and D out signal. Right? Inputs and inflow. So by the way, I'm extremely sorry, we forgot one point here. So the moment we are writing the data flow modeling is behavioral modeling, the output must be represented in the form of a registered data type. Okay, don't forget to write this one. If you forget this one, the output we cannot get. Register D out. That's how we need to write. Register D out. Don't forget to write this register data type for the output in the behavioral modeling. Okay. Next, the input is DAN clock, CLOCK clock. The output is D out. Okay, of course, output we need to write it in the register data type. Another method is something like this. You write register here also and D out. Okay, both methods I have shown. So it is possible to write separately or we can combine with the output also, something like this. Now, okay, fine. What is the logic here? What is the logic? Logic is here is whenever we find a positive edge of the clock, and the clock is a positive edge, the D out is assigned by DAN signal. See carefully. Whenever there is a positive edge, the D out is assigned with the DAN signal. For all other cases, for others, D out is assigned with the D out only. That means don't change the value of the contents. Okay, this is what the logic. So let us write this logic in our program. Okay. So since it is a behavioral modeling, we need to write always whenever there is a change in something. What is the change that we are expecting? What is the change that we are expecting? Edge we are expecting, right? What type of edge that we are talking about? Positive edge, right? So we have a provision that we are using the pause edge of pause edge. Positive edge can be represented by pause edge keyword. Okay, so the pause edge of the clock that we are going to talk about. Okay, so therefore there is a change of the positive edge. Whenever there is a positive edge change, then the following statement has to be executed. So what is the following statement? Whenever there is a positive edge is there, then what has to happen? D out is equal to DIN, as simple as that. D out is equal to DIN. That's all. Whenever we have a positive edge is finding that, then the following statement must be executed. DN is equal to D out. If the positive edge is not there, don't do anything. Whatever the previous value is there, let it be previous value should be there. Right? That's all. As simple as that. So finally we can write and module. Only single statement. Whenever we find a positive edge, this has to happen. If there is no positive edge, don't do anything. Just keep it whatever the previous value is there, the previous value will be retained there.
సార్ అక్కడ రెండు కన్నా ఎక్కువ స్టేట్మెంట్స్ ఇస్తే బిగిన్ అండ్ వాడాలి అంతే.
Yes. So whenever we are using the 2 or 3 more statements are there, then we write begin and end. So that's the reason why I quoted that point. If only one statement is there, begin and end is not necessary. Okay. So ikkada kuda begin and end module రాయలేదు కదా, forgot. So ఇక్కడ కూడా అవసరం లేదు యాక్చువల్గా. See, you can see here also. Finally I can write end module. If statement అంతా ఒకటే ఇక్కడ. Okay. So therefore I can write like this. It is not necessary. For simplicity, I'm writing the begin and end. If enable is true, D out is equal to DN. Altogether, this is one statement only. Okay, na? So ఇక్కడ కూడా begin and end అవసరం లేదు నాకు. I don't need begin and end here also. Since if enable is true, D out is equal to DN. Only one statement only. Okay, but the simplicity I have written the begin and end. if you have a difficulty of knowing that begin and end, for the time being you have to habituate to that begin and end. If you are comfortable, just if you have something like this, only one statement is there, no need to use the begin and end, right? So let us write the test benches in the next class. For this one, it takes another 3 days, 3 hours to complete this behavioral modeling. But this is the fundamental and basics for the behavioral modeling. Okay, so it's completely logic based one. Okay, so whatever the logics that I'll tell you, then you have to understand that logic and write the program for that. Okay, so with this we have completed the today's class. We will see in the next class. Thank you very much. If you have any doubt, please send me a mail, so I'll respond to that one.